A sequence of equal payments made at equal periods of time is called an annuity. If the payments are made at the end of each time period, and if the frequency of payments is the same as the frequency of compounding, the annuity is called an ordinary annuity. So this is a lot like when you get paid, you take a chunk of that pay and put it into a retirement fund. You're doing it at the end of your pay period, and we're going to assume in our case that the frequency at which I get those paychecks is the same as my frequency of compounding. So the time periods between the payments is called the payment period, and the amount of time from the beginning of the first period to the end of the last period is called the term of the annuity. So how long between you started getting these payments and when you're going to finally finish them off. So the future value of the annuity is the final sum of all those deposits along with the compound interest. So that future value is defined to be the compounded amounts of all of the payments compounded to the end of each of the terms. Now each one of those payments though we'll have to be careful because some payments to the annuity will have been of longer and will get more compound interest. Some will be in less often, they'll get less compound interest. As an example, let's take a short term of 4 years and we're going to deposit $1,000 at the end of each year for the next 4 years in an account that's earning 8% annually, and we're going to assume that it's compounded annually. So what I've done is I've made a little diagram here of those 4 years. The first year, the second year, the third year, and the fourth year. And I'm going to look at these payments that I'm making. So since this isn't an ordinary annuity, when I make my first payment, it's going to be at the end of the first period. So I make a payment of $1,000, so it's going to earn 3 years of compound interest. So that's going to be 1,000 times 1 plus 0.08 cubed. So that's going to be the first term, the first amount that I put into my annuity. At the end of period 2, I'm going to go ahead and put in another 1,000, but that's going to only be in for 2 years. So I'm going to get 1,000 times 1.08 squared, and now I add that into my sum. At the end of the third period, I'm going to get another $1,000, but it's only going to be in 1 year, so it'll get 1 year's compound interest. So that's adding on another 1,000 times 1.08. And then I make my last payment, 1,000. It goes in, but it doesn't earn any interest. So what I get here is a sum of 4 different terms here. And if you look at those terms carefully, you'll see that each one is a part of a geometric sequence. So if I divide the 1,000, 1.08 by the 1,000, I get 1.08. If I take 1,000, 1.08 squared and divide that by 1,000, 1.08, I get 1.08 again. Each one of the terms in this has been multiplied by 1.08, so that's our common ratio. If we go ahead and write this out as a sum, so we have 1,000, 1.08 cubed, plus 1,000 times 1.08 squared, plus 1,000 times 1.08 to the first power, plus 1,000, we can see that the A is 1,000 and that the R is 1.08. To find the sum of this geometric series, we want to find the sum of the first 4 terms, or S sub 4. So I'm going to go ahead and take that sum formula that I had before. I'll put in A equal to 1,000, R equal to 1.08, and N equals 4, and I'll work out this fraction. When I do that, I get that on deposit at the end of 4 years, I'll have $4,506.11. So the future value of this account is $4,506.11. So in general, let's see what happens to when I deposit a payment R and work out what the sum is going to be for that and see if we can come up for a formula for the final sum that I would have on deposit in the annuity or the future value of the annuity. So I'm going to list out N periods here. I've listed out the first 3 and then ... So that continues until I get to the nth one. And at the end of each period, I'm going to make a payment of R. That R is going to be on deposit for all these other periods. So if there are n periods total here and it's at the end of the first one, that means it'll be on deposit for n minus 1 periods. So I get R times 1 plus I, the interest rate per period, raised to the n minus 1. That's going to be the first term in my geometric series. At the end of the second period, I deposit my R and I compound the 1 plus I interest n minus 2 times. At the end of the third period, I'll deposit R and I'll multiply by 1 plus I to the n minus 3 because there's n minus 3 periods to go. I'll continue doing this until I get down to the very end of the nth period, in which case I put in R, and then that earns no compound interest. So what I have here is my geometric series. So I'll have R, and then R1 plus I, and then R1 plus I squared. I'll continue doing this till I get all the way up to R1 plus I to the n minus 1. So this is simply a geometric series with the a value being R and the little r being 1 plus I. If I substitute those values into my formula for the sum of a geometric series, I get R times the quantity 1 plus I to the n minus 1, that's in the numerator, and in the denominator I get 1 plus I minus 1. Doing a little bit of simplifying and moving things around, the easiest way to write that is that the sum of the value, the future value, is R times the fraction where the numerator is 1 plus I to the n minus 1, and the denominator is I. That's the formula for figuring out the future value for an ordinary annuity. So here I've gone ahead and written that down. And remember, an ordinary annuity, the key thing is you make your payments at the end of the period. So R is the payment that you make, I is the interest rate per period, and N is the number of periods that you have it on deposit. So suppose I deposit $300 at the end of each month into an account that earns 8% compounded monthly. How much will be in that account in 30 years? So I'm kind of thinking of this as a retirement thing. Each month I'm going to go ahead and put in $300. 8% compounded monthly, well, that'd be a reasonable thing for the stock market to do. From the information in the problem, my payment R is $300. My interest rate per period is 0.08 divided by 12. And since I'm doing this 12 times a year for 30 years, that means 360 periods. So I'll go ahead and substitute those values into my future value formula. And when I do that, I get 300 times the fraction where the numerator is 1 plus 0.08 divided by 12, that quantity raised to the 360 power, minus 1. And in the denominator, I have 0.08 divided by 12. If I carefully put this into my calculator, I'll find that what I'll have is 447,107 and 83 cents. Not a bad chunk of change to have when you've just been putting away $300 each month. Now, a different kind of way of thinking about this is a sinking fund. Before, I was putting in regular payments, and then I just figured out what I ended up with at the end. When I set up a fund to receive periodic payments to achieve a given amount in the future, that's called a sinking fund. So instead of making the payments and saying, what do I end up with? Here I'm going to know what I end up with, and I want to know things like how much should I be putting in to end up with that amount. So instead of 447,107 and 83 cents, suppose I want to end up with 1 million. What would my monthly payment have to be? What I know in my future value of an annuity formula is now I know the S, and I want to find R. So what I'm going to do is that big piece in brackets, I'm going to divide both sides by that. So on the left-hand side, I have S divided by the fraction where I have 1 plus I to the n minus 1 in the numerator and I in the denominator. So if I want to simplify that, I'd probably want to go ahead and flip and multiply that bottom fraction. When I do that, I get s times I on top, and in the denominator, 1 plus I all to the n minus 1. So if I put in the s that I want to end up with, the interest rate per period and the number of periods, this will tell me that the payment I have to make to end up with that. So let's go ahead and write that out, and now let's put in our values for the example that we've just started. So I'm going to put in for S, 1 million. My interest rate per period is 0.08 divided by 12. So 1 plus I becomes 1 plus 0.08 divided by 12. And I'm going to do that for 360 periods. And I'll finish off the rest of the formula by writing minus 1. So putting in the values, I see that I need to be putting in $670.98. If I do that, I'll end up with $1 million. Now, sometimes you have to be careful about these things because of the rounding. Sometimes what will happen is maybe this value, if you were rounding, would round down to 97 cents. But if I were to do that, I wouldn't end up with $1 million. So normally what you'll usually see is people will round up, because rounding up makes sure that you get at least $1 million. In fact, you'll probably get a little bit more than that.